In this video, we're going to talk about graphing exponential functions. An exponential function is a function in which the independent variable x is in the exponent rather than the base of the exponent. When dealing with an exponential function, it's important to know what the base of the exponent is. Well, let's start with the exponential function 2 to the x. It's exponential because x is in the exponent. We can make a table of values to see what this graph looks like. When we let x be negative 3, 2 to the negative 3 is like 1 over 2 to the positive 3. 1 over 2 times 1 over 2 times 1 over 2 is 1 over 8. Similarly, 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. And 2 to the 3 is 8. So we're going to plot these 5 points. We'll ignore the first one and the last one just for the ease of graphing them. And when we plot negative 2, 1/4, we get this black point here. When we plot negative 1, 1/2, we get this black point here. 0, 1 is here. 1, 2 is right here. And 2, 4 is right here. Now, we plot these 5 points, and then in blue we draw a curve to represent the curve y equals 2 to the x. And we see that the domain is x element of the reals. The range is any y value greater than 0. We see that there's a y-intercept at 0, 1, and there's a horizontal asymptote at y equals 0. The x-axis is a horizontal asymptote. So the curve will never touch the x-axis, but it will get infinitely close to the x-axis. Next, we consider the function y equals 3 to the x. We can make a table of values here. So letting x be negative 3, negative 2, negative 1, etc., all the way down to 3. If x is negative 3, then 3 to the negative 3 is the same as 1 over 3 to the positive 3. That's 1 over 3 times 1 over 3 times 1 over 3, which is 1 over 27. Similarly, 3 to the negative 2 is 1 over 9, etc., on down the list. Ignoring the first point and the last point, just because we can't easily plot them on this graph, we plot the other 5 points in black. And then we connect them with this blue ink curve. And when we do that, we get that the domain is x element of the reals. The range is y element of the reals such that y is greater than 0. The y-intercept is at 0, 1. And the horizontal asymptote is at y equals 0. And so we see that the curve y equals 3 to the x is just a little bit steeper, very similar, but a little steeper than the curve y equals 2 to the x. Okay? But it has all these other characteristics in common. Now, what if the base of the exponent is a fraction? What if we have y equals 1/2 quantity to the exponent x? Well, again, we'll make our table of values, plot the same x values. 1/2 to the exponent negative 3 is evaluated by inverting the base to 2 over 1 and then making the exponent positive 3. 2 over 1 to the positive 3 is the same as saying 2 times 2 times 2, which is 8. Similarly, 1/2 to the negative 2 is 4, on down the line. 1/2 to the 0 is 1. 1/2 to the 1 is a half. A half to the 3 would be a half times a half times a half, which is 1/8. Now, again, we'll ignore the first and last point, but plotting these other 5, we get these black points right here. And we can connect them with the blue curve. We can connect them with a curve like we do in blue. And we get that the domain is all real numbers. The range is all real numbers such that y is greater than 0. There's a y-intercept at 0, 1, and there's a horizontal asymptote at y equals 0. And we'll see that the curve is basically a mirror image of the curve y equals 2 to the x. It's just actually a reflection of the curve y equals 2 to the x in the x-axis. Y equals 2 to the x looks like this, and y equals 1/2 to the x looks like that. But notice on every curve we've done so far, these facts have all been the same. We'll try one more parent function. We'll try y equals 1/3 to the x. Well, we'll make a table of values using the exact same x coordinates we've been using. And when we let x be negative 3, 1/3 to the negative 3 is the same as 3 over 1 to the positive 3, which is 27. We evaluate all of these y coordinates, and then we're able to plot these 5 points. We ignore the first and last just because they're not easy to graph. And when we plot those 5 points, we get these right here, and then we can connect them with the blue, and we get a curve that looks like that. Now, you'll notice y equals 1/2 to the x and y equals 1/3 to the x both go this way. Y equals 2 to the x and y equals 3 to the x both go this way. And that's something that's common, is if the base of the exponent of the parent function is less than 1, positive but less than 1, we get a curve that goes this way. If the base of the exponent is greater than 1, we get a curve that goes this way. We won't deal with any bases that are negative in this course in terms of graphing. Well, staying consistent with all the parent functions we have so far, we see that the domain is all real numbers, the range is all real numbers greater than 0, the y-intercept is at 0, 1, and there's a horizontal asymptote at y equals 0. So, certain commonalities have come up in all 4 of our graphs of the parent functions that we've done so far. There's always a horizontal asymptote at y equals 0. There's always a y-intercept at 0, 1. The domain is always all real numbers. And the range is all real numbers greater than 0. Okay? Now, in this course, we will also deal with bases other than 2 or 3 or 1/2 or 1/3. But just know that the process is the same. You make a table of values for whatever the base of your exponent is, and you go about it the same way. Now, we're going to have to be able to graph transformations of exponential functions. So recall that in previous sections we've dealt with transformations of parent functions. In this section, we'll graph transformations of parent functions by first determining the base of the exponent. So for purposes of this list, we'll assume the base is b. So far we've had a base of 2, 3, 1/2, and 1/3. Next, after we figure out the base of the exponent, we're going to determine 3 key points that we'll put through this mapping formula. It's the same mapping formula we used before. xy maps onto x over k plus d and ay plus c. Now, the 3 key points that we put through that mapping formula will be -1 comma b to the -1, or in other words, -1 comma 1 over b. We'll put 0, 1, and also 1b. So if the base of the exponent is 2, we'll put -1 comma 1/2, 0 comma 1, and 1 comma 2 through the mapping formula. Now, it's important to note there's always a horizontal asymptote at y equals c. The reason for this is that the parent function has an asymptote at y equals 0. So when we put the value of y equals 0 through the second half of the mapping formula, y maps onto ay plus c, that gives us 0 maps onto a times 0 plus c. A times 0 plus c is 0 plus c, which is c. So 0 maps onto c, meaning that horizontal asymptote of y equals 0 becomes a horizontal asymptote of y equals c. So in other words, a horizontal asymptote originally at y equals 0 becomes a horizontal asymptote at y equals c. Every one of these exponential curves that we graph in this section will have a horizontal asymptote, and to know where it is, we'll look at the c value after we put the equation that we're given in the proper form. Now, the input of an exponential function is in the exponent. So that means the exponent is k bracket x minus d. Now, we always multiply the output by a and we add c. Putting all of this together, we get that the standard form of an exponential function about to be graphed is y equals a times the base to the exponent k bracket x minus d plus c. So like we did in previous units, we're sometimes going to have to manipulate the expression that we're given in order to come up with the algebraic values we need to be able to do the graphing. And finally, recall that sometimes one of those constant values of a, k, d, or c, sometimes they're not visible, so to speak. That means that they're at their default setting, so to speak. And the default settings of a, k, d, and c For A and K, it's 1 because this is a multiplicative identity. And for D and C, it's 0 because this is an additive identity. Okay? So let's do this example here. We're going to graph the function 1 minus 3 to the exponent 1 minus 3 times 2 to the exponent 1/2 x plus 2. We're going to state the coordinates of 3 key points, the domain and the range, as well as the equation of the horizontal asymptote. Then we're going to verbally state the transformations that were done to the parent function. Okay? So the base of the exponent that we were given is 2. Therefore, the parent function will be y equals 2 to the x. So that means the points on the parent function that we're going to put through the mapping formula will be -1, 1 over 2. Whatever the base is, it'll be -1, 1 over that base. So since the base is 2, it's -1, 1 over 2. 0, 1, and 1, 2. We're going to put these 3 points, which appear on this parent function, through the mapping formula. Now, we were originally given this function expression, 1 minus 3 times 2 to the exponent 1/2 x plus 2. We know we want to factor out the k, so it becomes 1/2 times, in brackets, x plus 4. We're still multiplying by -3, but this 1 is over here adding at the end. That tells me a will be -3, k will be 1/2, d will be -4, and c will be +1. And we put those up at the top of the page. Now we take our first point of -1, 1/2, and we put it through this mapping formula. X over k plus d, a y plus c. And when we evaluate this, we get -6, -1/2. Similarly, 0, 1 maps on to -4, -2, and 1, 2 maps on to -2, -5. Note, since we always have a horizontal asymptote at y equals 1, at y equals c, in this case that's y equals 1. So we make a note of that as well. And now we go to graph our curve. Well, first thing we do is we plot the points. We've got -6, -1/2. We've got -4, -2, and we've got -2, -4. Or sorry, -2, -5. Now, we also make a point of putting in our horizontal asymptote, which is always at y equals c, and in this case is y equals 1. We put that right there. And then we connect up these points, respecting the role of the asymptote, but still understanding that the curve is infinitely wide. It has a domain of x element of the reals. So the horizontal asymptote is y equals 1. The domain is x element of the reals. The range is y element of the reals such that y is less than 1. And then we can state our transformations like we did in previous units. We have a equals -3, so that means since it's a negative value, we have a reflection in the x-axis, and we have a vertical stretch by a factor of +3. We take the magnitude of that, vertical stretch by a factor of that. K is equal to 1/2. Well, what that means is we're taking every x coordinate and dividing it by 1/2. That means we're multiplying it by 2. This word factor means what did you multiply by? So it's a horizontal stretch by a factor of 2 when k equals 1/2. D equals -4 means we have a translation left 4 units, and c equals 1 means we have a translation up 1 unit.